Swayam Prabha. Digital India. Educated India.
Hello and welcome everyone to this course on gas turbines and jet engines. So, today is lecture 19, which is the fourth lecture or penultimate lecture of week 4. Okay. So, we were already discussing real gas turbines and we were discussing irreversibilities in the compression and turbine processes, and to calculate or incorporate the effect of these irreversibilities, we have defined two efficiencies, isentropic efficiency and polytropic efficiency. In the previous class, we have seen how the polytropic efficiency for a compressor is defined and how it is used for analysis. Today, we will see how the polytropic efficiency of a turbine is defined and then what is its role in doing the calculations or analysis. Okay. So, the important points that we will cover today are polytropic efficiency of turbines, how is it defined, then polytropic exponent and its relation with polytropic efficiency for turbines, similar to what we have done for compressors, but we will have different expressions and different derivations. And then we will again try to relate polytropic efficiency and isentropic efficiency, but this time again for turbines. Okay. Again we will give different efficiency values. So, remember the definition of polytropic efficiency. Polytropic efficiency we had defined as the isentropic efficiency of an elemental stage, within the process such that it is constant throughout the process. Okay. So, this constant is important. So, it is this elemental stage also is important. So, isentropic efficiency of an elemental or infinitesimal stage within the process such that it is constant throughout the process. Even for turbine that is true, but the way it has to be defined mathematically is different. Okay. So, if I have two constant pressure lines like this, let us say that this is the ideal process going from 3 to 4S, and this is the actual process going from 3 to 4. Okay. So, we will take a infinitesimal pressure ratio within the process, which we will draw in an exaggerated manner, but you get the idea. So, in this case the actual temperature difference going along the actual path, the temperature change is smaller than the ideal temperature difference. Let us say that actual temperature difference is dT and the ideal temperature difference, okay, in this case this will be equal to dTs. dTs is greater than dt. Okay, dTs is greater than dt. So, in this case the polytropic efficiency is defined as, so eta infinity to denote polytropic, T for turbine is equal to dt by dTs. Okay. This is different from the compressor where we had dTs by dt. Here it is dt by dTs, because dTs is larger than dt. Okay. So, this is how we define and it remains constant. It is seen that it remains constant throughout the process irrespective of what is the pressure ratio. Okay. So, now how do we relate it to known quantities like temperature and pressure, like in the previous case. So, we can start from the definition. Let us say that eta infinity C is equal to dt by dTs. So, this means that dTs by T. So, if I am following the temperature along the isentropic path dTs by T, okay, let us write separately. Following the temperature along the isentropic process dTs by T, this is equal to gamma minus 1 by gamma dP by P. From how did we derive this? This is from the isentropic relation for the ideal gas, because this we are following the isentropic path for Ts. Okay, we will write it in a better way. So, now we can replace this dTs in terms of dt and the polytropic efficiency. This is T, not C, okay, turbine. So, this will be dt by T 1 by polytropic efficiency of turbine is equal to gamma minus 1 by gamma dP by P. Okay. So, now after integration we can find that. So, I am jumping some steps, you can do the calculation, that efficiency, polytropic efficiency is given by log of. So, if I am going from 3 to 4, log of T3 by T4 natural log, of course, by log of P3 by P4 to the power gamma minus 1 by gamma. Okay. So, this is the efficiency expression for polytropic efficiency of a turbine, and again the importance of this expression is that this T3, T4, P3, P4 are measurable quantities. Okay. T3, T4, P3, P4, at the inlet and outlet we can measure this easily, which means that we can easily calculate what is the polytropic efficiency. Okay. So, this is the benefit of, apart from the fact that this remains constant, this is also an easy way to find the variation. Okay. So, next the efficiency, sorry. We will, similar to the compressor, we will now define a polytropic exponent for this turbine process, expansion process, and relate it to polytropic efficiency. So, for a process going from, let us say, from 1 to 2 or 3 to 4, because we are using that for turbines. So, we have already derived that infinity T is equal to ln T3 by T4. In the previous slide we had derived this, ln T3 by T4 divided by ln P3 by P4 to the power gamma minus 1 by gamma, ln P3 by P4 to the power gamma minus 1 by gamma. So, all within this bracket. So, which means that T3 by T4 is equal to P3 by P4, again similar to the case of compressor, although the expression is different, the process is similar, to the power infinity T gamma minus 1 by gamma. Okay. So, as if this is also a polytropic process going from 3 to 4, where the polytropic exponent n can be such that nt minus 1 by nt, where nt is the polytropic exponent. So, that is equal to the expression eta infinity T multiplied by gamma minus 1 by gamma. So, this is as if T3 by T4 is equal to P3 by P4 to the power Nt minus 1 by Nt, where Nt is the polytropic exponent for the process. So, this 3 to 4 acts like a polytropic process with the exponent Nt, where this value of Nt can be related to the ratio of the specific heat gamma and the polytropic efficiency as eta infinity T gamma minus 1 by gamma. Okay. So, we can also write eta infinity T in terms of both the exponents. So, this will come out to be gamma by gamma minus 1 by Nt minus 1 by Nt. Okay. So, this is how we define, and we can relate the processes, and that is why also it is known as polytropic efficiency, because the process is like a polytropic process. Okay. The actual process is a polytropic process where we can find the exponent from the other known conditions. So, the last point is that we want to relate the polytropic and isentropic efficiencies for a turbine. Okay. So, again we know that I will draw quickly because it is the same thing. Going from 3 to 4 S is the isentropic process and 4 is the polytropic or actual process. Okay. We know that isentropic efficiency is defined as T3 minus T4S in terms of the diagram, T3 minus T4, not T4S. So, actual work output by ideal work output, T3 minus T4S. Okay. So, this we can write by cancelling T3 from both the numerator and denominator. We can write this as 1 minus T4 by T3 divided by 1 minus T4S by T3. So, T4 by T3 is the actual process. So, we know that they are related. In the previous slide only we have defined. So, T3 by T4 is P3 by P4 to the power eta infinity T gamma minus 1 by gamma, if we run to write in terms of the efficiency. Okay. So, this is 1 by r to the power eta infinity T gamma minus 1 by gamma. Now, it is a known quantity at this point divided by 1 minus. So, this T4S by T3 is isentropic. So, we can write this as 1 by r to the power gamma minus 1 by gamma. So, this is the relation between the isentropic efficiency eta T. Okay, this is the isentropic efficiency. So, isentropic efficiency we directly write using eta and the subscript for the component. For polytropic efficiency we also add another subscript which is the infinity. Okay. So, like this. So, this is the relation between both of these. So, we have seen what is polytropic efficiency for compressor, we have seen what is polytropic efficiency for turbine, then we have seen how they are related to isentropic efficiencies, corresponding isentropic efficiencies, and we have also defined what are the polytropic exponents. We have seen that the processes behave like polytropic processes. We have defined the exponents and related it to the efficiencies. Now, we will try to solve a couple of numerical problems or examples. Before that, we can plot actually how this isentropic efficiency, which we have discussed that it does not remain constant with pressure ratio. So, in real life, if for a given polytropic efficiency, how the isentropic efficiency changes. Okay. So, at r equal to 1, let us say that the isentropic efficiency is, or let us say some value of isentropic efficiency is there. So, this will be equal to the polytropic efficiency. Now, with increasing value of r, the isentropic efficiency keeps on decreasing for a compressor. Okay. So, for a compressor, the isentropic efficiency keeps on decreasing. What about for turbine? For turbine, on the other hand, the isentropic efficiency keeps on increasing with increase of r. So, more the number of stages or more longer are the processes, will have higher efficiency as compared to that of a elemental volume. Why? Because part of the work which is which is lost in the previous stage can be recovered in the next stage. Okay. But for compressor, the opposite is true. Okay. So, this is also eta infinity t. So, like this we can get the variation, you can plot and find with increasing value of r, and they merge to the polytropic values at r equal to 1, which means that the pressure ratio is, there is no separate pressure ratio, it is equal to 1. Okay. Now, let us take a look at couple of numerical examples. Okay. So, let us say that example 1. We have a process, okay, we have an expansion process, okay, turbine expansion process. Going from 3 to 4. The conditions which are given are, at the inlet of the turbine, the pressure is 1000 kPa, all are realistic values. At the exit, the pressure is 100 kPa. At the inlet of the turbine, the temperature is 1500 Kelvin. And at the exit, the temperature is also known. We have measured the temperature and found that this is equal to 820 Kelvin. So, we have measured the inlet and outlet conditions for a gas turbine and found that these are the temperature and pressure at the inlet and outlet of this turbine. Okay. We want to find the values of polytropic efficiency of the turbine, the polytropic exponent for this process 3 to 4, and the isentropic efficiency for the turbine. Remember that these are different terms. So, this is N t and this is eta t. Eta t is efficiency, N t is the polytropic exponent. So, it is slightly confusing, but these are the standard notations. So, how do we proceed? So, if we are trying to solve the problem from scratch, it is better to start with the definition of polytropic efficiency. Okay, but because we have already derived this today, we will just use it from that point from where we have derived. So, from this point onward, but you should always start from the basic, from the polytropic efficiency definition, and do not try to use these as formula. Okay. These are expressions which are derived for analysis. So, after derivation, what we will get? We will get that eta infinity t is equal to ln T3 by T4. Again, I will remind that do not start with this as formula, derive this from the basics, ln P3 by P4 to the power gamma minus 1 by gamma. Remember gamma is 1.4, okay. Till now we are considering here. So, from this we can find what is the value. T3 is 1500, T4 is 820, P3 is 1000 and P4 is 100. Okay. So, this gives us a value of 0.918, which I have already calculated. So, you should calculate and verify that you get this same value. Okay. Whenever I am doing some calculation, to save time I have already done the calculation and writing the value, but you should pause the video and try to calculate and then compare your results and find whether these are correct or not. Okay. So, we have found the first answer, which is the polytropic efficiency. Next is polytropic exponent. Okay. So, again we know that, so from this relation from 1 we know that T3 by T4 is equal to P3 by P4. If we observe the polytropic efficiency within the power, then you have eta infinity t gamma minus 1 by gamma. Okay. So, we had defined the polytropic exponent as nt minus 1 by nt is equal to eta infinity t gamma minus 1 by gamma. From here we can substitute, we know what is the value of eta infinity t 0.918, gamma value we know. So, we can get what is the value of nt, and it comes out to be equal to 1.356. Okay. Again you should calculate, pause the video, calculate on your own, then verify the result. Okay. I am just writing down the direct value which I have calculated, which may or may not be correct, supposed to be correct, but you should verify always. And finally, we can get what is the, so this is the second answer, and you can see that it is slightly lower than the value of gamma. So, slightly lower than the value of gamma. Finally, we want to find out what is the polytropic efficiency, means what is the relation between isentropic efficiency and what is the value of isentropic efficiency. Okay. So, again we will, because we have already derived this, we can use this, but in general you should derive from scratch instead of taking this as a formula. Okay. So, better to start from scratch, because otherwise you will not learn the correct solving procedure. So, this is T3 minus T4s, T4 divided by T3 minus T4s. Okay. So, I can calculate from the isentropic efficiency, like the polytropic efficiency, or I can directly calculate what is T4s based on the pressure ratio and then find the value of eta t. Okay. So, both are open for us. So, you should try both and see that both give you the same value, and it comes out to be 0.940. Let me repeat again, one way is to find the value of T4s. How will we find? We know what is T3 and we will use the pressure ratio of 10, 1000 by 100. So, we will get what is T4s and then we will get what is the efficiency, because T3 and T4 are known. The second way is to use this value of polytropic efficiency and the relation between polytropic efficiency and isentropic efficiency to get the isentropic efficiency. Okay. So, like this we can find the value. Now, we will finish with another small example, which is just a continuation of this problem. Here the pressure ratio R was already given to us and it was equal to 10, 1000 by 100. Okay. Now, if for the same condition, keeping everything else same polytropic efficiency of 0.918, if the pressure ratio is 20, means 2 times, what will be the value of the isentropic efficiency. So, let us say that this is 3 and this is 4s and this is 4. Okay, and now the pressure ratio is 20. Okay, new pressure ratio is 20. So, for r equal to 20, all the other conditions remain same. So, n eta t, n infinity t, sorry eta infinity t is 0.918, which is the polytropic efficiency. By the way, you should compare the polytropic efficiency with the isentropic efficiency, and we have seen that for turbine this should increase from the polytropic efficiency. Okay. So, for the turbine this has increased with increasing r. So, we expect now that this should be slightly higher even when r equal to 20 as compared to r equal to 10. Okay. So, instead of here it will be somewhere around here, but it is higher than the elemental stage efficiency. All other conditions remain same. So, all other conditions remain same means the polytropic exponent also remains same. Okay. So, N t is equal to what was calculated 1.356. So, 1.356. Okay. So, now we can use this polytropic relation T4 by T3 for the polytropic process from 3 to 4. This is equal to P4 by P3 to the power N t minus 1 by N t. Okay. Everything is known here. P4 by P3 is 20. So, this is 20 to the power 0.356 by 1.356. T3 is 1500. So, this gives us a value of T4 equal to 683.16 Kelvin, okay, which of course should be lower than the T4 value in previous case, because now we have a larger compression, a larger expansion. And we can also find what is the value of T4s. How will we find the value of T4s? T4s by T3, okay, for this ideal process is equal to P4 by P3 to the power gamma minus 1 by gamma. This will give us a value of T4s, which is equal to 637.36 Kelvin. So, therefore, the isentropic efficiency of this turbine with pressure ratio 20 and same polytropic efficiency as previous is equal to T3 minus T4 by T3 minus T4s. You can calculate based on all the values are known. T3 we had taken as same as the previous case, which is 1500 Kelvin. So, this is equal to, it comes out to be equal to 0.947. Okay. How does it compare with the previous value? Previous value was 0.940. So, we see that it is indeed it has increased, which we expected that with increasing R it should be the case, okay, and that is what we are getting. So, we can see that the polytropic efficiency, if it is fixed, so in both these cases it was fixed and the same value, how the isentropic efficiency varies, and we also know how to do calculations and find temperature based on this polytropic efficiency concept. Okay. So, in this class we have defined and analyzed polytropic efficiency for turbines. Previously we had done for compressors. For turbines the calculations and analysis is slightly different. We have determined its relation with isentropic efficiency of a turbine and with the polytropic exponent for a turbine. And finally, we have solved a couple of numerical examples to get an idea about how to do these calculations and also to get realistic values of polytropic efficiency and isentropic efficiency and how they relate to each other, what sort of differences in values occur between these. Okay. So, these are the references, the important books that we are following, and with this we conclude this class. Thank you, and we will meet again in the next class. Thank you.